All right, so the last time we generated a regression model and we were able to estimate the model using OLS. We use Stargazer table that automatically beautifully shapes the entire results, okay? And then we also use generalized least squares, okay, which was indicated here. Generalized least squares will always not bring R square. They will rather bring log likelihood, Akaike information criterion, Bayesian information criterion there. These are like the kind of the similar to the R square for testing the fitness of the model, you know. And then we also estimated a feasible GLS, which is the weighted least square. And then we estimated the transformation, whether it is log linear or log log or log level or level or, you know, but we saw that the best of all of them is this log linear. You can see that the log linear here is better than the log log. Why? Because when you look at the log urban, the location urban, you will see that that one is significant compared to the log log. The log log, the location urban is not significant, even though all the others, you know, are similar. And then finally, we looked at the newer West standard error. Okay. If you could remember carefully, the newer West standard error, that one was correcting for the heteroscedasticity and autocorrelation. In case you've forgotten, let me just remind you a little bit by going backward here. Okay. So this was all of the transformation. This last one here, this was a command. This command was a command that gave us a newer West. Okay, watch it carefully. It will correct for the heteroscedasticity, which is here. And it would also correct for the autocorrelation. Okay. So the standard errors are replaced. And once you replace the standard error, remember, we always have the coefficient. The coefficient divided by the standard error will give you the t statistic or the t value. Okay, the t value is now deduced, it's now calculated. Using the t value, you can now find the p value, which will tell you whether the variable is significant or insignificant. Okay, so what the newer West did was to replace the standard error. It cannot do anything to the coefficient. It replaced the standard error with a lower level standard error, a smaller standard error. So that when you divide the coefficient by the standard error, the t statistic becomes bigger, which then makes the p value smaller. And that was done. And once you do that, that is how come we can see that the coefficients are what? Are all significant. Look at it here. It's the most one with the most significant coefficient. You can see that let me show you something. This is beautiful, I'm telling you. You can see that in this context, the coefficients are the same as original. Check it. So the coefficients have not changed, unlike the weighted least squares, which will have, okay, or feasible generalism, which will have, you know, change coefficient, or even the log linear one, which will have change coefficient. And this one, the coefficients are the same, but you look at the standard errors are smaller, you know, smaller, very small, and in this case, even zero. Okay, zero, or maybe not zero, but approximately zero. Okay, in all of these, and that's why we got a very significant result. All right. So now today, what we want to do, so that was for heteroscedasticity. What we want to do now is we looked at what you should do when it comes to feasible GLS. Okay. We looked at all of them. We concluded here that instead of the feasible GLS, you can rather use the OLS but correct for the standard errors using the newer West. So that was our final point. Today we want to look at a new topic known as autocorrelation. You've already heard about it, but what we are going to do now is to understand it. Now you got to remember that, and by the way, I know I didn't set you a question on the autocorrelation. Okay. I didn't give you a question on that. I wanted to, but because I have not taught you this, I decided to omit that. However, you will use that, in your term paper, so it's important you understand. We usually assume that the errors in a regression model are independent. What errors? This is a cross-sectional model, so the errors being independent here means you have error epsilon I and you have error epsilon j. So let's say you have a data set and the data set is made up of the quantity demanded of gene betas for store 1. So these are the stores, store 1, store 2, up to 40. The quantity is maybe 220, here is 190, and then all the way up to, something, let's say 150. And then you have the price, and then you have other variables. And then finally, you have an error. And the error here is error 1, error 2, error 3, up to error 40. Okay, so there's an error. And this error is the difference between the predicted and the actual. The predicted kill and then the actual kill. Okay, or the observed kill and the fated kill. Now, so this error and this error 1 and this error 2, they must not depend on each other. So a store number 2, its error should not be influenced by store number 1's error. That is a whole principle of that. There should not be association between them. If there is an association, autocorrelation has happened. If there is an association, if the disturbances, okay, the disturbance terms are related to any of the observation, okay, and influenced by the disturbance of the other observation, then we say that autocorrelation of the residuals, has occurred. So the errors of one observation should not be affected by the errors of another observation. If they are affected by another, serial correlation has happened. But you should also note that it can happen in a cross-sectional data and it can happen in a time series data. In cross-sectional data, the influence of an increase of one family. So let's say that you have a family in East Legon, okay, and then the income of that family went up. Okay, that family's income has gone up. And that increase in their income led to a higher consumption expenditure. So they started consuming a lot. They bought brand new cars, they bought 2 new houses and all of that. That should not motivate the consumption of another family in cantonment. It should not motivate them to also, because they too, their income has gone up, then they too are going to also make the consumption purchases of things. They should not, if they are doing it on their own, that is fine, but they should not be doing it because they know that their other family friends in East Legon are doing that. That, when they do that, then we say that there is autocorrelation of the consumption expenditure. So that is when you have cross-sectional autocorrelation. Time series autocorrelation is when there's a disruption. Let's say that there's a labor strike. Labor union has gone on a strike and it's affecting 1/4 of the company's maybe production level. So maybe between the January to March, there was a strike and profit came down significantly. And then there was no strike throughout the year. And yet that very strike that happened between January and March has led to a downturn in the profitability of the company even towards December. Like it has carried on or it's carried over to the other period. When that happens, then we have autocorrelation of the errors, because it shouldn't influence something else that happened. But you know, certain things in life are like that. It can carry forward. And that, ladies and gentlemen, is the meaning of autocorrelation, practical meaning of autocorrelation of both cross-sectional and time series. Let's take a practical graphical example. So if you look at this thing here, okay, if you look at the first one, there is a clear pattern among the errors. Okay, if you look at the pattern here is cyclical. It goes up, it falls down, it goes up, it falls down, it goes up, it falls down. There's a clear pattern, okay, a discernible pattern. And that kind of pattern where, you know, there is discernible pattern means that there is autocorrelation. Now, this is between the errors and time. So, and I'm using time series autocorrelation. I'm not looking at cross-sectional autocorrelation yet. This is another example, okay, between the errors over time. There's again a clear upward, you know, pattern, trend, okay, according to the errors. The more the time, the errors are increasing. And that shows that the residuals are exhibiting autocorrelation. If you look at this one, it's quadratic, but again, even though it's quadratic, it's linear. It reaches a top, it begins to fall, it is showing a quadratic trend. The moment it is showing that quadratic trend, it means that there is autocorrelation in there. But look at this last one here. There is no clear autocorrelation in this case because you can't say that this thing is rising and falling in any way. If you look at this first one, it rises, it falls again, it flattens, it rises, it falls. Like there's no clear pattern. And look at it. And in this case, there is no autocorrelation. That's a good thing because errors must not exhibit a certain pattern. It's like when the thing has happened, a strike action has happened in the first quarter, and you can see that same result happening again in the last quarter. That's a pattern, and we shouldn't detect that. So these are graphical demonstrations of autocorrelation. Now, autocorrelation is an interesting concept. And there is a name for the first order autocorrelation. Remember, like I said, we have both cross-sectional one and then time series one. What is the difference? Now, the errors follows a first order autoregressive scheme. And when it follows a first order autoregressive scheme, and I'll explain it with you, so don't worry, then you can write it like this. So if you check, there's an epsilon I. So this is just the error. We are looking at how the error itself is not dependent. Sorry, it's not independent. It's dependent on something. So you can see that this is the error. This is for cross-section. That's why you have I. I here is indicating individual factor. So the error of a particular store or a particular company or a particular country or a particular individual, that error here is influenced, look at it here, it is influenced by the error, epsilon j, of another individual. And the influence is being backed up by this symbol there. So by how much the error of j is influencing the error of I is determined by this, you know, coefficient, the marginal effect. Of course, this latter part here is basically the stochastic noise. Okay? Other factors that are, you know, noises, you know, that may affect the errors, which are not even discernible. So this is for cross-sectional data. But for time series, you have this blue one. So here you have the error of time t being affected by the error of time t minus 1. So in this case, you are looking at something, the error from last year affecting the error of this year. And the value of its effect is the rho, that Greek letter rho. So the rho here is a coefficient of the autocovariance, okay? Or the marginal effect of the past year's error on the present year's error. That's it. The value of the row should be between -1 and +1. Okay, that's the value. And our goal is to know the value. Once we know the value, we will know whether or not there is autocorrelation. So remember, you need to know the value of row. We'll come to that. What are the assumptions of this error T? The error T should be independently and identically distributed. Okay? Independently and identically normally distributed with a zero mean and a constant variance. Okay? So the error is the basic error that we know of in a normal regression, the stochastic noise. It should follow that same trend. Okay. Another thing you want to notice that the variance of the error, remember this one is talking about the mean of the error. So the variance of the error should be homoscedastic. Okay. It should be homoscedastic. But the only thing is that in this context, it is correlated not only with its immediate past, but it's also correlated with the various several past. So see, the first order autocorrelation was when you have this epsilon t correlating with t minus 1. But the epsilon t can also correlate with epsilon t minus 2. And it can also correlate with epsilon t minus 3. And it cannot, and you can look at it like the strike action I spoke about. The strike action for the first quarter affected productivity in the first quarter. That same strike action in the first quarter affected productivity in the second quarter, in the third quarter, in the fourth quarter. Okay, so it means that the error is now affecting, the error of quarter 4 is as a result of what happened, or the error in quarter, the previous quarter, or quarter 0. And that is the point that we are looking at. That's a clear indication of autocorrelation. Okay, what does it mean when rho is 0? Well, when rho is 0, it simply means that the residuals are not autocorrelated. Now, why is that so? Let's go back and mathematically you see. Go back to this equation. If this rho here is 0, if this rho here is 0, then you have 0 multiplying what? The whole of this epsilon t minus 1. And that means that the error becomes purely what? Stochastic noise. And so we don't have any autocorrelation. And that is cool. Okay? So rho should be 1. But hey, life is not a straight line. Rho can sometimes not be 1. If rho is more than 1, it means that the residuals are positively autocorrelated. If the rho is less than, if the rho is more than 0, that is if they are positive, we have positive autocorrelation. If the rho is less than 0, we have negative autocorrelation. If the rho's are positively autocorrelated, then it means the variances are underestimated. That's it. They're underestimated, and that will affect the F statistics, the T statistics, and all of them because they will be overestimated when they shouldn't be. Okay. How do you detect autocorrelation? One easy way is to use residual scatter plot. So scatter plot the residuals. And then how do you detect it graphically? Well, if the errors are independent, that is if there is no autocorrelation, then you will notice that the residual should look randomly scattered around the 0. That's a clue. Remember this one here? You can see that they are randomly, don't forget, randomly, not a pattern, not a trend. It must be random. They must be randomly scattered around the 0. And you can see that on the positive side, they are all up and down the 0. Okay. And that is a clear indication that there is no autocorrelation. But if we see a clear pattern, cyclical pattern, upward pattern, downward pattern, quadratic pattern, exponential pattern, then it means that autocorrelation is there. It means that serial correlation is there. So let's try one. And then we'll see the thing. How do you test it? How do you test it? Okay, you see, one thing is detecting it, another is testing it. What's the difference? Detecting is done graphically. Testing is done using a statistical test. And there are several methods that you can use to test the presence or the absence of Autoco in the residuals. There are several methods. One of them is a visual inspection, using the plot. But then, see, one thing about visual inspection is you use an inspection, something called autocorrelation function. Okay. Autocorrelation function. You use that plot. Autocorrelation function plot. We'll look at that very soon. You can use that to check the presence of autocorrelation. Okay. So this is where you are graphing the correlation of time series with the lags of the time series. So you take the epsilon 1 t, then t minus 1, then you plot all of them in the residuals. That's it. The second approach is you can use the Debye-Watson test. And the last approach, you can use a Lange box test. So all of these will agree with each other, and then you can say that there is no Autoco or there is Autoco. All right, let's take the Debye-Watson test, for example. How do you test? How do you test? Well, every test statistic requires you to follow 4 steps. Step number 1 is to formulate the null and alternative hypothesis. Step number 2 is to calculate the test statistic and compare it with a critical value. Test number 3 is to find the p-value and compare the p-value with the alpha. Alpha is the level of significance. Test number 4 is to decide and to conclude. Step number 4, decide and conclude, statistically and practically. You decide and conclude statistically and practically. So step number 1 is to formulate the null hypothesis. So the null hypothesis is that there is no autocorrelation or there's no first order autoregressive scheme. That's it. That's the way you write it. Then the opponent or the alternative hypothesis will say that, oh, hang on, the rho is not 0. The rho can be, towards -1 or towards +1. So autocorrelation is present. That is a hypothesis. If we get a lower p-value, then we can reject the null hypothesis of no autocorrelation and conclude that there is autocorrelation. How do you do that? You use a Debye-Watson test. Look at the Debye-Watson test very carefully. It looks manya, but it's very simple. So first of all, you need to have the errors of the current time period. And you know that even in R, it can give you all the errors. Excel can also give you the errors. Then you subtract the previous period's error from the current period's error. Then whatever you get, you square it. That squaring will bring the numbers it would clear the negatives that will be there. Because if there is a negative value here and you square it, it becomes positive. You now divide that by the current period error square. Again, if this one is negative at any point, it will become positive. Once you've gotten this value, that gives you the Debye-Watson. Now, what is the maximum value you can get for the Debye-Watson test? What is the minimum value you can get? Well, we can prove something interesting, that when the Debye-Watson is equal to 2 into bracket 1 minus the rho, remember the rho is taken from this formula here. Okay. This formula is finding the rho. And this is the one we said that when the rho is 0, then the whole of this thing will be what? 0. So the error will be the usual stochastic noise, which is 0. So if rho here is 0, then it means that the Debye-Watson is what? 2. Check it. If rho here is 0, then you have 1 minus 0, which is 1. 2 times 1, which is 2. So the Debye-Watson will be 2. And when Debye-Watson is 2, that is perfect good news, because that means there is no autocorrelation. That point is here. If rho is 0, then the Debye-Watson is 2. So there is no autoco. But if rho is moving towards 1, remember the maximum value of rho is 1. The minimum value is -1. If rho is moving towards 1, let's say it is now 1 completely. Look at it here. If it is 1, you have 1 minus 1, which is 0. 0 times 2, which is 0. So the Demonstration will be what? 0. And in that case, you have a positive autocorrelation, 0. I'll show you a chart and you see this. If the rho is -1, okay, so if this one is -1, you have 1 minus minus 1, which is 1 plus 1, which is 2. So you have 2 times 2. So it means that this Demonstration will be what? 4. And when it is 4, you have a negative positive autocorrelation. So the autocorrelation can be positive or negative, and either one of them is not good. You want to know autocorrelation. So here is a chart that gives you a feel, okay, a feel, okay. And there are 2 critical values. Remember, the test statistic is calculated using the 2 critical values, and the critical values are given in this range. Look at it. Where it is 2, it is you accept the null of no autocorrelation. Oh, hold on. Yeah. You accept the null of no autocorrelation. So watch it. It's not exactly 2, but anything around 2. So what is around 2? I'll put it here. Okay. Around 2 here means anything 1.5 to 2.5 is good. It's a good sign that there is no autocorrelation. Take note. Okay. Anything, because here is 0, right? So if here is 0, and look at here is 2, it means that 1 is somewhere in between this and that. Okay. So here is like 1.5, okay, and if here is 2 and here is 4, then the 3 is somewhere here, okay, which means that 2.5 is somewhere there. So between this and this, which is the acceptance region, is between 1.5 and 2.5. Guys, I hope you're understanding me, aren't you? Okay. So that's a very, very beautiful way to assess autocorrelation. Autocorrelation is a very interesting area. Okay, so now check whether there is autocorrelation. Now, if you think there is autocorrelation, if there, not you think, if you test and you realize that there is autocorrelation, or if you use a graph and you think there is autocorrelation, test it using the Deborah-Watson test. We've said that. We are going to try that in our R, and then we can come out with some level of conclusion. So let's go to our R data set. Okay, remember we've been dealing with this data set called Brukutu. And we used to have gene multi. You can remember gene multi. I'm going to show you this gene multi. This was a model. Let me just run the model. There is it. It's shown here. Gene multi. This was original model. Original, which we manipulated, blah, 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 blah. Okay. So that's a gene. Oh. So that's a gene multi. Now we are going to check whether there is autocorrelation in this or not. If there is, we'll handle it. If there is not, so the first thing to do is to take this LM test. We run this LM test. It's a library package. Install and run it. So here I'll say
please, are you showing the R?
Oh yeah, it's not showing, eh?
No, we are still seeing the PDF.
1 second, please. Please confirm if it is showing. Wow.
Okay, it's now showing.
Okay, let me just quickly go back. Okay. So this was a command I ran, the old one that we did, on this Brukutu data set. So this was a command. You remember gene multi equals to LM for linear model. Q is a dependent variable with a tilde symbol. Then you have the price plus the complement price plus the income plus the location, which is a dummy, occupation, which is a dummy with 3 levels, religion, which is a dummy with 3 levels. Then we summarize the result, and then we got this. This was the original model. Okay. Now I want to check whether this model is having autocorrelation. This model was a very good model. If you can remember, the R square was 99%. Approach adjusted R square was also similar. So we are going to install this package, okay, and and then we will invoke it, install and invoke it. I have installed it. I'm just going to invoke it by running it. And then we will run the Debenwaston command. The Debenwaston command is it's just a test for autocorrelation of lag 1. Okay, so it's a first order autoregressive scheme. You can do for lag 1, you can do for lag 2, and all of that. So let's check the value. Okay. It appears that I'm supposed to run the LM test. Let's see. If the LM test is there. Yeah, is there. Okay. So let's try it again. Oh, could not find the function there. All right, so sometimes some of these functions, let me just run the car command and see. So there are two commands here. Now it's working. So it looks like you need to use this car first. Okay. It looks like you need to run this car package first. Okay, so you can see that you have the autocorrelation, the p-value is almost 6%. Okay. But first, let's check the test statistic. This is a test statistic. It is 1.3 approximately. Do you remember the rule of thumb? Let me just go back here. The rule was that for it to have no autocorrelation, there must be what? Between 1.5 and 2.5. And what we have here is 1.3. So it means that there is some evidence of autocorrelation in there. And the fact that the p-value is even 6% it means that whatever we have here is not significant at 5%. Okay. So that is a first possible sign of autocorrelation. Let's run with this command too. DW instead of the full Debenwaston. DW. Again, the test statistics is the same, 1.3. This time, the p-value is 3%, which means that whatever we found here was significant, which means that whatever we found here is 1.3, and that 1.3 is truly significantly, outside the zone. Okay, so we can say with statistical proficiency that there is some level of autocorrelation in this. There is some autocorrelation. We are moving, towards negative, actually. Okay. But actually, right now, as it is, it's inconclusive. In fact, that's the best judge because it's actually between DL and DU. So the lower bound, the DL is the lower bound, the DU is the upper bound. And anytime it falls here, it's a zone of indecision. So the test is inconclusive. We cannot fully say that there is autocorrelation or there is no autocorrelation. It's inconclusive because of the range where and it is, statistically speaking, it is inconclusive. Okay, so at this stage, you can just use that to just say that, you can make your case that based on the inconclusivity, I will say that there is none if you want to go ahead with that. So that is one way you can check for the autocorrelation. There's another way you can use to calculate. There are several ways. You see, all of them are giving you the same test statistic. Okay? The same test statistic. The p-value is similar, so 6%. They are all telling you that it's inconclusive. And then you can check for other lags. Okay? You can do the long jump box, this one. Okay? With the lag of 5, you can see you can have the lag of 5, you can have the lag of 20. That means that you have t minus 1, t minus 2, 2 minus 3, minus 4, minus 5. You're looking at whether it has some relationship with the past 5 years. Okay. You can use the long jump box because what the long jump box is doing is that it helps you to check for autocorrelation up to n number of lags, unlike the Debenwaston. Let's do that. And again, when you did that, you can see that the p-value is approximately that. It doesn't tell you much about the number, we don't have lags, as you can see. In our own, we have only cross-sectional data. So we cannot have lags, in our own to make any. Box PS is also another one that one can use to be able to test for the autocorrelation of the residuals. Okay. It also does a similar one. There are several tests, of autocorrelation. You have the Bridge-Pagan test, a Bridge-Godfrey test, which works also in the presence of lagged dependent variable, unlike the Devin-Wesson. And it also leads to the same conclusion. Let's check that. So all of these are indicative of the fact that the autocorrelation is inconclusive. Generally. But hey, what if it's there? Okay, what if it's there? All of these points, you can run them. I've run all of them. All of these, I've run them. Okay. What if it's there? But remember that if you look at the box PS1, okay, with a lag of up to 5 that I've done here, the box PS, but I don't know why this was 20, but you can do 5. Let's do 5. Okay, so that's it. If you look at this, okay, with a lag of 5, you will notice that given the 1% or 1.3%, it means that we may be tempted to reject the null hypothesis of no autocorrelation to say that there's some modicum of residual autocorrelation in the work. Okay. You can use that, but again, like I told you, we don't have a lot of years in our work. But what if it's there? What if the autocorrelation is there? Well, other tests you can use to do the autocorrelation is the Bridge-Godfrey, the Akakis-Schwarz information, all of these things. You can use them to do that. Right? But the most important thing I keep saying again is what if is there? How do you deal with it? It's an error issue. It's an error issue. So you have to check whether there has been some variables you should have added but you did not add. Okay. So sometimes you have to remove some of the independent variables and replace them and run a template and TC. We were doing that with heteroscedasticity. And if that kind of omission does not help to eliminate the autocorrelation, then it transforms the variables. You remember that even in heteroscedasticity, we're transforming the variables. So the variable transformation, the same variable transformation approach we use there, you can use that. How? By converting them from log level to log linear, or from log level to log, or from log level to log all, and all of that. That's what I mean by transformation. You can also use the weighted least square and then the GLS, which we did for the heteroscedasticity. And we already know that we use a newer West that was controlling for both heteroscedasticity and autocorrelation. So you can use the same newer West when it would handle both at the same time. You can use that to do the work. The measures for the autocorrelation, the transformational measures, these are other transformations you can use. One of them is a Cochrane-Ocott procedure, Hidrett-Lew procedure, and first differences procedure. You should learn some of these things on your own if you have to correct for possible autocorrelation. But like I said, what is the best one? Still use the OLS, the old guy, and correct for the standard errors. In the process of doing that, you use a newer West standard errors, which is going to correct for the both autocorrelation and heteroscedasticity. And this is why it is known as, robust standard error. That's a heteroscedastic autocorrelated consistent standard errors, or simply the newer West standard errors. But there's one thing you should note about using the newer West. Okay, it's very valid in large samples. It may not be useful in small samples. So when your sample is small, less than 30 thereabout, you should be worried in using the NWSE. So let's go and correct it. If you have only 15 to 20 observations, then the sample are small. But if you have 50 or more, the sample is big, and so good. Okay. Ours is 40, so let's try. Let's use a robust neural west. We've done it already. So I'm going to go here and run this robot neural west. Okay, I need to invoke a command, which is a library foreign, library LM, and library sandwich test. I just did that. Now let's do the robust neural west. And there you go. It's done. And if you want to show the results, remember that we always try and show the results, using that table. If you want the results, I just highlight this and then you'll get the results. And you can see that the p-values are all showing, significant, 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 significant. Okay. So it tells you clearly that they're all showing. The coefficients haven't changed. They're still going to be the same thing. And that is a very, very nice way. You can generate all of the results that we have in that regard. So neural west, as it stands now, for this is a very good way to handle autocorrelation and heteroscedasticity. Okay. So ladies and gentlemen, that brings us to the end of the principle and the concept of autocorrelation for this. Next time we meet, we are going to start looking at panel data econometrics. We are going to look at panel regression models and then how important these are in econometric studies.